Hello students, I'm Professor Kumail Lakhani from Vidyalankar, and today I'll be covering a small concept of transformers. Now you'll must have had a small idea of transformers which you'll have studied in your 12th standard electromagnetic induction, where you'll actually study that transformer is basically a device which is responsible to transfer electrical power from one side to the other side without changing the frequency. And in the process, what it does is that it somehow steps up the voltage of the current or steps down the voltage of the current. This is a basic functionality of my transformers. Now transformers again is a big topic present in BEE. So I'll be just giving a rather small story about transformers. We'll be looking at it in a little more precise manner, wherein I'll simply be explaining as to why exactly are the iron losses in the core of the transformer constant. It's always seen that the core losses of the transformer are always constant in nature. It's the copper losses which vary. Just for your knowledge, this transformer is designed, if it has to be designed, it simply has copper windings on the primary and the secondary side, and it has an iron core, wherein it's believed that the iron core always have constant losses. Now those iron losses relate to flux, which is induced in the core of the transformer. Okay? So how exactly does this whole functionality work is what we'll be looking at into a little more precise manner. And initially what I've done is I've taken an input supply over here, some input voltage. This is an alternating supply, because of which what we're seeing is that when this supply is induced, there is some current which is going to flow. Since the supply is alternating, the current that is going to flow is alternating. Let's say I'm initially considering some current, that is some current IO, which is termed as your magnetizing current. Now when this magnetizing current flows through the windings of the coil, Faraday specifies that an EMF is induced across the coil. So I've just induced an EMF across the coil. Now let's say this Faraday mentions that an EMF is induced. Then eventually you'll also study Lenz's law, wherein it was stated that the magnitude of the EMF induced opposes the supply polarity. So let's say if I consider the initial supply polarity to be plus minus. So obviously with respect to Lenz's law, the supply polarity for the EMF induced, the EMF polarity for the EMF induced is going to be opposite to the supply polarity. Now because of this, what is seen as a field is going to be generated, and because of this field being generated, this whole core is going to be magnetized. So let's say the whole core gets magnetized and a flux is induced across the whole core, which is going to be present in this direction, which I've considered to be some flux phi. Now what is seen is that because of this flux, in your 12th standard you must have studied that, the concept of mutual inductance. So what is seen is that since the supply is alternating, the EMF induced is alternating, the flux which is generated is an alternating flux which is generated. So what is seen is that ideally the secondary side of the transformer is very close to the primary side, because of which what is seen is that there is a lot of mutual linking. So the flux which is generated is by default alternating in nature. Now this is a coil which is stationary, across which the flux is continuously moving, because of which what is seen is that an EMF is generated on the secondary side of the coil. This is nothing but basically the concept of mutual inductance that you all see. So that is the reason why what we see an EMF E2 is generated. Now what is seen is that EMF is generated. Now for the current to flow across the secondary side should be connected. As of now there is no secondary side connected, hence there is no current that is going to flow on the secondary side. This is what I had studied in the 12th standard till now. Okay? But there was no specific mention about those losses. As of now I know there's only one flux, which is the dominant flux present in this transformer. Now what I'll do is, I'll simply connect a load. Let's say I connect some load. Can be anything. Let's say some load, fan, light, your household connectivities, anything goes through a transformer. Now what is seen is that as I connect a load, what is seen is that the secondary side of the circuit becomes complete, because of which now a secondary current is going to be generated. Let's say some current I2 is generated like this. Obviously it's going to flow in this direction. Okay, undoubtedly it goes unsaid that the polarity of E1 and E2 are going to be the same, because E2 is not generated because of some supply. So Lenz's law doesn't apply. So magnitude of E1 and the polarity of E1 and E2 are going to be exactly the same. Hence the current is going from a high potential to a low potential, hence current flows in this direction. Now current is going to flow through the load, it's going to generate a polarity across the load. Let's say this is plus minus. Current is flowing in this particular manner. So it flows through the load, supplies some current to the load, and that current is going to come back again now. Okay? Now this current is an alternating current, because this whole thing is basically on alternating signals. Hence the current that is generated also is going to be alternating in nature. Now analyze carefully, the same current which comes in is now going to flow back into the secondary windings of the coil. Current is alternating, the alternating current flows back into the secondary windings of the coil, implies an EMF is going to be generated of its own. Previously it was generated because of E1, but now since this alternating current is going to flow across the winding, it's going to generate its own EMF. Because of it, it's going to generate its own respective field, correct? So let me assume that because of the current I2, there is a field which is generated, which I consider to be some field phi2. Some flux is generated, and that flux is what I'm considering to be some flux phi2. Now what is seen is that previously there was just one dominant flux in the core of the transformer. Now there's another flux which is present, and both are opposite in directions. Why? Because the direction of currents are opposite in nature. So because of this, because of this newly generated flux, this original flux is going to get weakened. Now since this original flux is going to get weakened, this flux was generated because of E1. So if this weakens, let's say this weakens, obviously proportionally E1 is going to weaken. And since E1 and V1 are parallel in nature, always what we see is that if I'm neglecting the losses, V1 should be equal to E1. So proportionally, if because of the generation of flux phi2, phi weakens, E1 is going to weaken. If E1 weakens, proportionally V1 also should be weakened to maintain this equality amongst both the sides. Because this weakens, to generate equality, this also should proportionally weaken. But what is actually observed is V1 is an independent supply. Come what may, V1 is not going to weaken. Why? Because it's an independent in nature. Come what may, it's not going to be dependent on anything. So what is only going to happen in the process is that this is not going to weaken, this is somehow not going to come down. So the only alternative left is that the proportional weakening, V1 is simply going to somehow strengthen that proportional weaken, that it comes back in power with respect to V1. So proportionally, the weakening generated because of this flux phi2, V1 is simply going to send an additional component of current. Let's say that current component is some current I2 dash. The reason I'm considering this to be I2 dash is because E1 was weakened because of phi2. Phi2 was generated because of I2. So if V1 has to strengthen E1, obviously it's going to send an additional component of current, because of which an additional EMF is generated, which proportionally increases E1. And hence what is seen is that since you're looking at the proportional relationship, the current I2 is exactly equal to the current I2 dash. Only thing is they are exactly opposite in directions. Now because of this current I2 dash, what is seen is that E1, the proportional weaken is going to be proportionally strengthened, that it comes in power with V1. Because of which now this additional component of current I2 is again going to flow through the windings. It's going to generate its own flux. Correct? And so let me assume that flux that it generates is some flux phi2 dash. Some flux it generates, which I consider to be phi2 dash. Now if you analyze very carefully, what you see is that the flux phi2 and phi2 dash are exactly equal in magnitude and exactly opposite in direction and exactly equal in its densities. Why? Because of I2, the proportionally weakening generated to flux phi, which generated a proportional weakening to E1, eventually was responsible to send an additional component of current I2 dash, which eventually generated a flux phi2 dash. So what we understand from here is that I2 dash and I2 are exactly opposite in direction and equal in magnitude, because of which the fluxes that it respectively generates have to be exactly opposite in directions and equal in its respective densities. Because of which what is seen is that in the core, the flux phi2 and phi2 dash eventually cancels out, keeping the original flux phi, the dominant flux, present in the core of the transformer. And all the losses in the core are simply connected to your flux. So as the flux changes, the losses changes. But then by this explanation, what we actually analyze is that the flux remains constant. And since the flux remains constant, what we also analyze is the I losses present in the core of the transformer also remains constant. I hope you enjoyed my video.